Hello, this is Professor Matt Katroulis of Rio Hondo College, and here I'm going to present Chapter 13, which is on the subject of carboxylic acids, esters, amines, and amides. Now this is going to be the last of our 4 chapters in organic chemistry. The chapters before this were focused on general chemistry, and the chapters after this are focused on biological chemistry. So Chapter 13 essentially continues what we were already studying with Chapter 12 by focusing on organic compounds which contain heteroatoms. In particular, we're going to continue to focus on compounds which contain carbon-oxygen double bonds, specifically carboxylic acids, esters, and amides. Now, amides contain nitrogen atoms as well. And so we will also look at amines, which contain carbon and nitrogen. And as we're going to see here, amides are going to be the products of the reaction between carboxylic acids and amines. So there's going to be a fundamental relationship between those groups. We will also find that this chapter focuses quite heavily on acid and base chemistry as it relates to organic compounds. So let's start off with naming of the carboxylic acids. And it is very similar to what we've seen in the previous chapter. In particular, it's very similar to what we will see with aldehydes. So the first thing we want to do, as always, is identify the longest chain of carbons which contains the functional group, the carboxylic acid. And we call that, again, the parent hydrocarbon. And the carboxylic acid will always be at the end of a chain and be numbered number 1. And because it's always numbered 1, you don't need to number it at all in the name. The ending of the parent hydrocarbon goes from ane to oic acid. And in pretty much every other way, the naming of compounds here is the same as for the previous functional groups. Now, we will often see carboxylic acids abbreviated as COOH or CO2H. Your textbook in particular likes to use the first version of that. So if you see that, you should immediately interpret that as a carboxylic acid. Now, these are the rules according to the systematic system, what we call IUPAC rules. But we find that some of the carboxylic acids have common names that we should be familiar with. And they are these 3 compounds here. So this carboxylic acid here has only 1 hydrogen, and it is called formic acid. You might recall from the aldehydes chapter that when we had 1 hydrogen here and 1 hydrogen here, that was called formaldehyde. So form is another way of saying essentially 1 carbon. Formic acid is what is contained in ant bites and what gives them their sting. Here we have acetic acid. Acetic acid is the common acid in vinegar. And then finally, this acid with the benzene ring is called benzoic acid. Let's take a moment to practice naming a couple compounds here. So I've already gone ahead and numbered some of these compounds that I'm showing as examples. So if we look here, the first thing we would do is locate the functional group. The carboxylic acid is the functional group. We then look for the longest carbon chain that contains that functional group, and it's 1, 2, 3, 4. Not 5, because that's a chlorine. So 4 would mean that the parent name is butanoic acid, right? Butane for 4 carbons, butanoic acid for the carboxylic acid. But there is a substituent, the chlorine atom, and that is on carbon number 4. And recall, we always list substituents first in the name. So the name of this compound would be 4-chloro-butanoic acid. How about this compound? Here we have a carboxylic acid, COOH. We look for the longest chain that contains that carbon. So if we go this way, 1, 2, 3, 4, that would be 4 carbons. If we go this way, it's 1, 2, 3, 4, 5. So the longest chain is 5 carbons. And what that's going to mean, of course, so I'm going to go ahead and highlight everything in that chain, is that anything that is attached to it is a substituent and needs to be named as such. So what is that substituent? It's 2 carbons long. We would call that an ethyl group. So the name of this compound is 2-ethyl for the substituent, and then 5 carbons would be pentanoic acid. 2-ethyl pentanoic acid. Esters are a bit trickier to name. Their namings deviate the most from the usual rules. What we're going to do in naming esters is you first find the alkyl group, which is bonded directly to the oxygen atom. Now there's 2 oxygens in esters, at least, and this is the oxygen which is single bonded to carbon. So we're going to look at the other group that's on that side, the alkyl group. So we identify that first, and that's the first part of the name. And then we name the rest of the compound, which is called the acyl group, as if it was a carboxylic acid. And instead of ending in ic acid or oic acid, we change the name here from ic acid to ate. So ate is the ending. Now, naming esters can get very complicated, so I'm going to only consider rather simple esters in this particular class. And so I will not look at any esters that have substituents on them. They're only going to have one of the 4 common groups attached to the oxygen, the 4 ones being methyl, ethyl, isopropyl, or propyl, and then regular chains for the acyl group. So for example, they'll be based on say propanoic acid or butanoic acid or pentanoic acid. I find that it's easier here if we start with just a diagram to break down the various pieces. So we have here the carbon-oxygen double bond to the oxygen. Whatever is attached to that is called the alkyl group. And then this whole thing, everything left over, is technically the acyl group, but I'm going to just consider this group that's attached to that carbon to be the acyl group for now. Alright, so let's look at this compound here. It's clearly an ester because it's got the carbon double bonded to oxygen, and then that carbon's bonded to an oxygen. And then, unlike a carboxylic acid would have a hydrogen here. This is bonded to another carbon. So we first identify the alkyl group. So 2 carbons long. That alkyl group is ethyl. So that's going to be the beginning of our name. Now we look at this next part and we pretend it's a carboxylic acid for a moment. So pretend there was a hydrogen there. What carboxylic acid would this be? Well, 1, 2, 3, 4. 4 carbons long, it would have been butanoic acid. And as I said, we changed the ending from ic acid to ate, ate. So butanoate. So now we just put the alkyl group and the acyl group together. So the name of this compound is ethyl butanoate. Let's take a look at another compound. Again, it's an ester. You notice that I've drawn it in the same way as this drawing is right here. I've chosen to draw the oxygen to the right. Incidentally, there's no rule that says the oxygen here must be drawn to the right. It could have been drawn to the left. It could have been, the whole compound could have been drawn upside down. It's your responsibility to identify the various groups based on where they are positioned compared to the double bond oxygen here. So this is the alkyl group right here, the group bonded to the oxygen, and that should be very familiar. That is a methyl group. Now let's look at the rest of the molecule, and we pretend there's a hydrogen there for a second. And what carboxylic acid would that be? Well, we saw that one just a moment ago. It was one of the carboxylic acids with a common name. It was benzoic acid. So we changed the ic acid to ate. So benzoate. So we just combine those two words together and we get methylbenzoate. Let's go ahead and take a look at some of the properties of the carboxylic acids. Well, the most important property to call out is the fact that it has an OH group, and we know that OH groups are going to be able to hydrogen bond. Incidentally, I just wanted to call attention to the fact that we do not call it a hydroxyl group when we're talking about a carboxylic acid. Now, since carboxylic acids are able to make hydrogen bonds, what is that going to mean? That's going to tell us that molecules of carboxylic acids are going to be quite strongly attracted to one another. And we find that when there's strong intermolecular forces, that we have to have high boiling points and high melting points in order to separate those molecules from one another. And so they're going to be relatively high for compounds of their particular size. We find that carboxylic acids with generally few carbon atoms, usually less than 6 carbon atoms, are going to be soluble in water. And again, that's largely owing to the fact that these molecules can make hydrogen bonds. Now, it is also true, incidentally, that we find carboxylic acid molecules often paired together. This would be if we were able to look at them from the submicroscopic level. And we call these pairs dimers. Di stands for 2. We're going to see Di coming up in the next chapter with carbohydrates when we talk about disaccharides. Di just means forming a group of 2 here. And so again, how does that affect their boiling points? In order to separate these molecules from one another, that's what we have to do when we're boiling. You have to break the hydrogen bond attractions, and that requires energy. So this increases the boiling points of carboxylic acids. What about esters? Well, here I have a carboxylic acid on the left, and here I have an ester on the right. First of all, let's look at both of these compounds quickly before we get into too much detail about the esters. What is the geometry on these carbon atoms? Well, look at the carbon and how many atoms it's bonded to. It's bonded to 1, 2, 3 different atoms. That's the same for both of these. And therefore, and has no lone pairs. Carbon makes 4 bonds. So bonded to 3 atoms, no lone pairs. We call that the trigonal planar geometry or shape, bonded around there. And the bond angles, recall, for all of these should be close to 120 degrees. What is the relationship between these two compounds? Well, if we look carefully at this, you'll notice that we have a CH3 on this side and an H on this side with the acid. It kind of looks like I've just switched these two groups. So they have exactly the same number of each type of atom. 2 carbons, 2 oxygens, and 4 hydrogens. So the relationship between those is they are isomers. And specifically, they are what we call structural isomers. Now, they have exactly the same molecular formula, but that does not mean that they are going to have the same properties. Specifically, they're not going to have the same boiling point and melting point. Which of these compounds would have the lower boiling point and the lower melting point? Well, we know that's based on intermolecular attractions. As we already saw, carboxylic acids can form hydrogen bonds, and hydrogen bonding is the strongest type of intermolecular force. What about esters? Well, esters can receive the hydrogen part of a hydrogen bond. They do have lone pairs on the oxygen. But what about all their hydrogens? This hydrogen is bonded to carbon. These hydrogens are bonded to carbon. There are no hydrogens bonded to fluorine, oxygen, or nitrogen. So you're missing one of the two important components that you need in order for there to be hydrogen bonding. And so this compound cannot form hydrogen bonds. Its intermolecular forces are going to be weaker than for the carboxylic acid. Incidentally, what kind of intermolecular forces do esters form? Well, does it have a dipole moment? Sure, it does have a dipole moment. We've got oxygen atoms pulling away the electrons from the carbon side. So electrons are being pulled away. There's definitely a dipole moment. So dipole-dipole forces are the strongest intermolecular force that we have with esters. Since carboxylic acids have stronger intermolecular forces than esters, we would expect carboxylic acids to have higher boiling points and the esters to have lower boiling points. Now, why did I choose these two particular compounds to compare? They were isomers. They have the same molecular weight, so that makes for a totally fair comparison between these two compounds. Are they going to be soluble in water? Well, we already know acetic acid is definitely soluble in water because that's essentially what vinegar is. Vinegar is acetic acid dissolved in water. What about the ester? Well, the ester can't really hydrogen bond, but it should be just polar enough that I might expect this compound to dissolve in water. And in fact, it very likely would, because it contains not very many carbons, and it is able to form hydrogen bonds with water due to the fact that there are lone pairs there. However, if there were more carbons added to either the alkyl group or if there were more carbons added to the acyl group, it would very quickly become quite nonpolar and probably would not dissolve in water. Now, unlike several of the other functional groups, for example, the thiols and the amines, which we'll be talking about soon, we find that esters generally have pleasant smells. At least some of the smaller ones do. And many of them are in fact exploited for that purpose, used for food additives or perfume materials or anything where a pleasant smell is needed. So here are some examples of esters with fairly pleasant smells. Let's go ahead and name these. So again, we'll notice that this is the alkyl group right here. So this is ethyl. And this has how many carbons? 1, 2, 3, 4, 5, 6. So that would have been hexanoic acid. So it's ethyl hexanoate. And ethyl hexanoate has the smell of pineapple. How about here? This group is a little longer than we're used to for an alkyl group, but it shouldn't be too hard to name. It's 1, 2, 3, 4, 5. So that would be derived from pentane, so pentyl. So just like this was ethyl, this is pentyl. And this also has 5 carbons on this side. So that would have been pentanoic acid, which becomes pentanoate. So this is pentyl pentanoate, and it has an apple smell. And then finally down here we have ethyl, and this is derived from benzoic acid, so that would be benzoate. So ethyl benzoate, which has a wintergreen smell. Now, it should come as no surprise from the name that carboxylic acids are in fact acidic. And of the functional groups, they are the most acidic that we normally are going to encounter. The second most acidic we've already studied, and that was phenols. They are weak acids, and what does that mean? Well, again, weak acid means weak electrolyte. It does not dissociate completely in water. Very, very little of it actually dissociates, which means it does produce some H+ ions in water, but mostly does not break down, unlike strong acids like hydrochloric acid or sulfuric acid. However, if we add a strong base, like sodium hydroxide or potassium hydroxide, because it's an acid, it will react easily with those. It will lose its hydrogen to form water and a salt. Now, the cation of the salt is simply the cation of the base. So if we use sodium hydroxide, it's going to form a sodium compound. Potassium hydroxide, it forms a potassium compound. the carboxylic acid loses its proton, its H plus ion, and then the anion will be everything that's left over after it's lost that H plus. So the OH becomes just an O minus here. Although I haven't drawn it out, the oxygen, recall, usually has 2 lone pairs. Here it would have 3 lone pairs and 1 bond, in addition to a negative charge. So let's look at a couple examples of these. So, well, first of all, we'll look at generic reactions. So I've used R here to stand for just some generic alkyl group. This is a carboxylic acid. I've color-coded in red all the different species that are going to form the water in the reaction. So this proton here is lost, and this hydroxide come together to make water. And we're left over with sodium, and which is going to have a positive charge, that's the cation, and this oxygen, which is going to have a minus charge. Same thing here, except here I'm using potassium hydroxide. And so here we get the sodium salt, and here we get the potassium salt. But in all other respects, these are exactly the same reactions. Now, let's talk a little bit about the properties of salts. We know that carboxylic acids are generally soluble in water, particularly small ones. And small, again, just means low molecular weights, not too many carbon atoms. Should salts be more soluble in water or less soluble? Well, while it's true that carboxylic acids can form hydrogen bonds, ionic compounds should be even more soluble in water. We know that a lot of ionic compounds, in fact, are soluble in water. So water is polar. Ions are very, very quickly going to be surrounded by water molecules. So I would definitely expect the salts to be more soluble. If there are many, many carbons in the carboxylic acid, then even the salt might not be soluble. But they're almost always going to be much more soluble than the carboxylic acids they came from. Salts are named very similarly to esters. So instead of there being an alkyl group, we just say the name of the cation, either sodium or potassium, as the case may be. And you can see it looks a lot like an ester in terms of its structure, the way I have it drawn here. So we just say the cation and then the acyl group. So for example, this compound here, it is a salt of a carboxylic acid. What carboxylic acid? Well, imagine the hydrogen is still there. 1, 2, 3 carbons. That would be propanoic acid. Propanoic acid. So that just becomes propanoate. So the name of this is sodium propanoate. Same idea over here. We have the potassium. So it's going to be potassium. And then what carboxylic acid would this have been if the hydrogen was still there? It would have been benzoic acid. So this becomes benzoate. Potassium benzoate. And I'm going to go ahead and end here for this first lecture in Chapter 13. When we come back, I will start talking about some applications of these, starting off with soap.